Hello, teammates. It's your host coming to you from the physics bunker. You'll be seeing this on the 27th of March. And today I want to take a look at some key aspects of what you read in section 22-5 in Walker with loops of current and magnetic torque. When we get into a later section, and Walker identifies this as well, this is the fundamental principle of electric motors. We're just going to introduce it, and then in the next section, we're gonna explore that some more. Next section being the next section in Walker, maybe a week from now. So let's look, and I'm going to take you through some examples and explain why this is. We're going to solve this two ways. So we're going to determine magnetic torque. So we know that magnetic fields generate magnetic forces on charged particles. We know that electrical current is driven by the flow of electrons, which are charged. And so wires carrying current in a magnetic field are going to feel a force. And in a simple loop. Now, again, it's not our problem to figure out how we get a square loop of wire. It's not to be contradictory. That's kind of a common term, a square loop of wire. How we get that charge to flow, it's not our problem. So here we got a B field going from left to right. We've got a current going clockwise. And so we know it's going to generate a force. Now, we can ignore a couple things. We can ignore, let's label our wire segments A, B, C, and D, with this dashed line being the center between. And the example I'm going to use is it's got a dimension of 0.3 meters on a side. We've got a current of 3 amps, and it's in a magnetic field of 0.5 Tesla. So for A and C, the wire is not going to feel any force because we've got the charge flowing. It's moving, but it's moving parallel to the magnetic field, and so it's going to give us a sine of 0 degrees, which is 0. So ILB, so for the force is going to feel the velocity, the sine theta is 0, so it's going to feel 0 force. So A and B, segments A and B are going to feel no force at all. So our torque's going to come from segments B and D. And so using our right-hand rule, I'm going to do D first. Current's running this way. Mag field's running to your right. So it's going to feel a force down into the page. I'm going to use our symbol force down for segment D. And for segment B, current this way, field to the right is going to feel a force up. And we're going to use the symbol for that up force. And so if we had an axis here and it could spin, the wire would spin like this. It's going to feel a force up and a force down. It would spin like this. And we get into motors, we're going to talk about why that is. So that kind of sets us up. There's two ways to solve problems like this. It's not really in your equation sheet. You can derive it, but it's kind of easy money, right? Because you know from your veteran experience in AP Physics 1 that torque is force times radius. And we know that we can determine our magnetic force from ILB, current, length, mag field, that's our force, times our radius is going to give us our torque. And so the radius here, it's not going to be 0.3. Our radius is going to be from how that would turn on its axis of rotation, if it had an axis of rotation. And we're gonna just talk philosophically here, so we can solve it using that. So the other way to solve it, and we're gonna solve it both ways this morning, or whenever you're watching this, there's a sweet derivation in Walker, how he gets to another one. He looks at current times length, or he gives it a height, times the mag field, times 1/2 the width, plus, for the second one, 1/2 the width again. And so height times width is area. Yeah. So height times width is area. IAB over 2 plus IAB over 2, which gives us IAB, current area mag field, equals your torque. That's a pretty clever way to get at this. Let's do a couple quick problems. Let's solve this first one using the first technique. So your torque is going to be 3 amps times your length, because these lengths don't matter. This length, either way, 3 amps times 0.3 meters times 0.5 Tesla. Sine 90 is 1. And we're going to multiply that by 2. And here's why we're going to multiply it by 2. We got a force coming up this way. We got a force going down that way. Those forces are complementary. They're going to add. They're going to cause that rotation. And so we're just going to, it's going to be the same on both sides. We're going to multiply that by 2. It's going to give us our total torque. Wait a minute. I forgot to put my length. Times 0.15 is our lever arm, times 2. So our lever arm is 0.15. We're going to solve that. Solve this once. 0.0675 newtons times 2 is going to give us 0.135 Newton meters. Sorry, this should be Newton meters as well. So that's solving it the first way for torque. Second way, using the area. So torque equals current area mag field. Sine theta, 90 degrees in both cases is 1. So 3 amps times area, 0.3 meters times 0.3 meters times 0.5 Teslas gives us the same thing. 0.135 Newton meters. Same thing. We'd expect that. It's good. Now, as this loop rotates, the torques are going to change. The torques are going to change. In fact, if you imagine this is your loop and it rotates, when it comes up like that, it's going to change as it goes around. So we're just looking at this for that one instant. If you want to look at figure 22-17 in the book, he does a good explanation for how that torque's going to change, because your lever arm is going to change, yeah? So your lever arm, as your loop rotates, your lever arm gets shorter and shorter and shorter till your lever arm's got zero width, essentially. It's vertical. And so what happens is your inertia continues to move that loop until it starts picking up that torque on the other side again. I think that's good, teammates. We'll talk to you soon.